Alright guys, in this section, 6.6, Exponential and Logarithmic Equations, I want you to first off, before we get into solving logarithmic equations, make sure you take note and realize that the homework assignment is a altered version of what was given in class. So a lot of these problems are the same as what was given in class, but not all the problems that was given in class are on this list. For what we're doing in the rest of the class, what I have here on this video is all you need to be completing. And I know this section is exponential and logarithmic equations, but we're going to go ahead and start with logarithmic equations. So what we're talking about, this is just an equation where there's a logarithm inside of it. So log base b of x with a variable inside the logarithm equaling y. And it's important to realize with logarithmic equations that we're going to need to check our answers because we can't have a negative base and or a base of 0, and what's inside the logarithm, x in this case, has to be greater than 0, which means it has to be positive. It can't be negative and it can't be 0. And solving exponential and logarithmic equations is very similar. Step 1 in this case is going to be to condense the logarithm. So we want to get the logarithm as simplified as possible. And then step 2 is going to be we're going to remove the logarithms by doing one of two things. We're going to either use the common base property, which says this: log base b of x equals log base b of y. So if we have a logarithm with the same base on both sides and the two logarithms are equal to each other, then what's inside the two logarithms has to equal each other. Okay, so this is very similar to the common base property for exponentials. What says if you have a logarithm that has the same base, we can drop the logarithm and then what's inside the two logarithms must equal also. So that works if you have a logarithm on both sides of the equation. If you don't have a logarithm on both sides of the equation, the other option is we can convert to exponential form. Okay, and when we convert to exponential form, that will remove the logarithm. And then from there, we just finish solving it using whatever appropriate method or methods are needed. And I've got 3 examples here. So this first one here, 2 log base 5 of x equals log base 5 of 9. We see that we have log base 5 on both sides. However, this one is not condensed. If you remember in the logarithmic properties video, we had the property that said log base b of x to the y power is equal to the same as y times log base b of x. So that property said that if you have a power, the power gets brought to the front of the logarithm. Okay, so the fact that this 2 is in the front being multiplied means that this 2 is technically can be condensed back into a power, and we can rewrite this equation as log base 5 of x squared equals log base 5 of 9. And this is an example where we can use that common base property. Since we have log base 5 on both sides, and it's a one-to-one comparison, we can cancel them. And that would tell us that x squared is equal to 9. And then from here we square root both sides, which gives us that x could equal positive or negative 3. Now, remember at the beginning of this video, I said up here, what's inside the logarithm has to be a positive number. Okay, the x is inside the logarithm here. So, although when I plug in positive 3 here, this would be 2 log base 5 of positive 3. That's allowed to happen. We can have a log of a positive. But if x is equal to negative 3, we'd have 2 log base 5 of negative 3, and this is undefined. Okay, so then even though when we square root we get positive negative 3, the only one that actually is an answer is 3. Okay, x equals negative 3 is what we typically hear as being an extraneous solution. Okay, it's an answer that we find algebraically, but it doesn't check. So, in that case, the only answer to this problem would be positive 3. Now, if we look at this example over here, log base 5 of x plus 6 plus log base 5 of x plus 2 equals 1. The first step is to condense the logarithm. Okay, so since we have 2 logarithms here, and if you guys remember in the last video, we had this property that said log base b of m times n equals log base b of m plus log base b of n. So if we have 2 things multiplied, it expands into 2 logarithms being added. So the fact that these logarithms are being added means we can condense it back into log base 5 of x plus 6 times x plus 2. Okay, so we can convert that back into a multiplication problem. Now at that point, we can't use the common base property because we don't have a logarithm on both sides of the equation. So in this case, what we're going to do is we're going to use the second technique that says convert to exponential form. Log base 5 of x plus 6 times x plus 2 equaling 1 would convert back to exponential form as 5 to the first equals x plus 6 times x plus 2. Sorry guys. So this would convert back to 5 to the first power equals x plus 6 times x plus 2. And then that gives us 5 equals, multiplying this out gives us x squared. 2x and 6x makes 8x. And 6 times 2 is 12. And then since this is a quadratic, the appropriate method is going to be to isolate it. X squared plus 8x plus 7 gives equal to 0. And then since there are factors of 7 that make 8, x plus 7, x plus 1. We're going to solve by factoring, and we get that the two answers are negative 7 and negative 1. Now, just because these are both negative doesn't mean that it's no solution. Notice here, if I plug negative 7 in here, log base 5 of negative 7 plus 6, I get log base 5 of negative 1. And the fact that there's a negative 1 inside the logarithm means that x equals negative 7 is an extraneous solution. Now, if I plug negative 1 into this first one, log base 5 of negative 1 plus 6, we get log base 5 of 5. Well, that's okay. We're allowed to have that. And actually, in fact, that equals 1. And then if we look at the next one here, log base 5 of negative 1 plus 2. Negative 1 plus 2 makes 1, which is positive. That checks. And in fact, a logarithm of 1 will always equal 0. And we see that these two, 1 plus 0, does in fact make 1. So it checks. So x equals negative 1 is indeed an answer. Okay, so just because you get a negative number doesn't mean it's not an answer. It's only not an answer if when you plug it into the logarithm, it results in a negative inside the logarithm. Okay, and then the last logarithmic equation we're going to go over is this last one here. Natural log of x equals the natural log of x plus 6 minus the natural log of x minus 4. Now you might be tempted to say, well, can I just cancel the natural logs since there's 1 on both sides? Now we're going to do that first. We are going to do that, but the first thing we're going to do is we're going to condense this. Okay, we had this property in the last video that said if we have a division, it expands out to a subtraction. We're going to use that property in reverse. So this is going to be the natural log of x equals, this would be the natural log of x plus 6 divided by x minus 4 because of the minus. And then now that we have a one-to-one comparison and they both have a natural log, we can cancel out the natural log, and our equation is going to be x equals x plus 6 over x minus 4. And then solving with the appropriate method, and this would be, is since we're dealing with a fraction, we're going to times both sides by x minus 4 to get rid of the denominator, x minus 4, which is then going to give us x squared minus 4x equals x plus 6. And then that's a quadratic, so then we're going to minus the x and the 6 over and get x squared minus 5x minus 6. And then this factors to x minus 6 and x plus 1. The factors of negative 6 to make negative 5, which means our two answers are 6 and negative 1. And then guys, here, running through this whole process of checking is not something you have to do, but let me just show you this. If I plug 6 in here, that's a positive number, so that's okay. If I plug 6 in here, 6 plus 6 makes 12. 12 is a positive, that's okay. If I plug 6 in here, 6 minus 4 is 2, that's also a positive, that's okay. So when I plug 6 in, I have no negative issues. If I plug negative 1 in, that's going to be immediately natural log of negative 1. which that can't happen. So -1 gets thrown out of the mix in this case, and the only answer to that problem is +6. And guys, that's the extent of the logarithmic equations for this class. The second part of the video is going to be exponential equations. So this is going to be b to the x equals y, where x, our variable, is an exponent, which is what makes it an exponential equation. And like I said, guys, you'll see that this is very similar to what we just did with logarithmic. So step 1 is going to be to isolate the exponential, get it by itself, and we'll go over that when we do an example. And then we're going to remove the exponential by doing one of two things. We're either going to convert to logarithmic form, and then use the change of base formula, or we're going to take the natural log of both sides and use the power rule. Okay, and remember, the power rule says that no matter what the log is, if you have something to a power, that power can get brought to the front of the logarithm. Okay, and you can do either one of these and you'll get the same answer. And then I forgot to put step 3 here. Step 3 is going to be to solve by appropriate methods. So I'm going to do the first couple ones both ways just to show you. So like this first one here, 2 to the x equals 5. The exponential is already by itself. You'll notice the second one here, 8 times 3 to the x equals 5. We're going to have to move that 8 first. But in this case, exponential is already isolated. We're going to convert this to logarithmic form. So we're going to use this by using the first step, which is convert to logarithmic form. And converting this to logarithmic form would be log base 2 of 5 equals x. Okay, and so we've got x by itself, but then if we want to figure out what does log base 2 of 5 equal, we got to use the change of base formula. And that change of base formula said this: if we have log base a of x, this can be changed to log base b of x divided by log base b of a. So it just says whatever the base is goes on the bottom. So for example here, log base 2 of 5 can be converted to log of 5 divided by log of 2, or we can convert it to natural log of 5 divided by natural log of 2. So if we go to our calculator now, since log of 5 and log of 2 are both base 10, we can punch that in. So we can go log of 5, close parentheses, divided by log of 2, and we see that the answer is roughly 2.3219. Or similarly, the change of base formula says we can change it to either base. So if I do natural log of 5 divided by natural log of 2, you'll see that we get the same answer. So this is saying if I take 2 and I raise it to the 2.3219 power, I should get approximately 5. And we can check this. So 2 to the 2.3219 power gives us approximately 5. Hold on, buddy, I'm recording a video. No, you can't help me with this. Alright, and then the second method is 2 to the x equals 5. The second method says take the natural log of both sides. So the natural log of 2 to the x equals the natural log of 5. And then we're going to use the power rule. So since the exponent's a power, we can bring the power to the front. And this is going to be x times the natural log of 2 equals the natural log of 5. And then to solve for x, we divide by natural log of 2. So we get that the answer for x is the natural log of 5 divided by the natural log of 2. And we see that that answer matches what we got over here when we use the change of base formula. Now you can use whatever method you want, guys. I'm going to just go ahead and tell you that taking the natural log of both sides and applying the power rule is the most widely used method, and it gets us to the answer in a little bit more quicker fashion on most of the problems that we're going to do. So going over this next one here, guys, 8 times 3 to the x equals 5. First step is to get the exponential by itself. We're going to divide both sides by 8. So we're going to have 3 to the x equals 5/8. And then now, to get rid of this exponential, what we're going to do is we're going to take the natural log of both sides. So the natural log of 3 to the x equals the natural log of 5/8. We're going to apply the power rule, which gives us x times natural log of 3 equals the natural log of 5/8. And then we're just going to divide by the natural log of 3. So we get that our final answer is the natural log of 5/8 divided by the natural log of 3. And then to get the decimal approximate, we'll just bring in the calculator. Natural log of 5/8 divided by the natural log of 3. And we get negative 0.4278. Unlike logarithms, we can have negative powers. So getting a negative answer with an exponential equation is not an issue. So the answer is negative 0.4278. And once again, guys, you could check this. If we come in here and we do 8 times 3 to the negative 0.4278, we should get approximately 5, which we do. Okay. So, and you wouldn't have to use the natural log. You could take the log of both sides. So, for example, you could, instead of doing the natural log of both sides, you could just do log base 10 of both sides, and you'll get the same answer. Most textbooks you'll see uses the natural log, and I honestly think the only reason is it just requires one less letter to write or type, and so it's just a little bit quicker when we have to write out our response. But in all honesty, that's the only reason I know that we use natural log rather than log base 10. And then the last one here is probably the most complicated one. It just requires a little bit more time to work it out. 5 to the x minus 2 equals 3 to the 3x plus 2. We have an exponential on both sides, and they're both isolated. If we had a problem like this, 5 to the x minus 2, and then let's say we had plus 6 equals 3 to the 3x plus 2, that problem becomes exponentially, no pun intended, more difficult. And on a problem like this, we would actually probably just use like Desmos and let technology take over the work for us to get the answers without actually solving it manually. Because what you could do on Desmos is you could just type in each side of the equation, and it would create 2 graphs, and then just identify where they intersect, and that'll tell you the solution to the equation. But for what we're doing in this class, guys, we're not going to get into that. 5 to the x minus 2 equals 3 to the 3x plus 2. Both exponentials, both isolated. So what we're going to do on this is we're going to take the natural log of both sides. And then we're going to apply the power rule. So this is going to be x minus 2 natural log of 5 equals 3x plus 2 natural log of 3. From here, we've got variables on both sides. So what we're going to do is we're going to do the sugar property. And we're going to get x natural log of 5 minus 2 natural log of 5 equals 3x natural log of 3 plus 2 natural log of 3. And we're going to move everything that has a variable to the same side. So we're going to minus this 3x natural log of 3 to the other side. And since the 2 natural log of 5 doesn't have an x, I'm going to move it to the other side. And so what we get is we get x natural log of 5 minus 3x natural log of 3 equals 2 natural log of 3 plus 2 natural log of 5. And then on the left side, since these both have an x, but they can't be combined because the logarithms are different, what we're going to do is we're just going to do factoring. We're going to do GCF factoring. We're going to factor out the x. And we did this very similar earlier in the year when we were solving like rational equations. Same concept. when you have two variables that can't be combined, you bring the variable to the front using factoring, and then now that variable is attached to this binomial through multiplication, so we're just going to divide it over. So, as weird as it seems, our answer for this is going to be the quantity 2 natural log of 3 plus 2 natural log of 5 divided by the natural log of 5 minus 3 natural log of 3. None of this cancels, none of this reduces. Now, you could type this in the calculator exactly how it's read, or you could clean it up a little bit if you wanted to. So, for example, we could rewrite this as natural log of 3 squared plus the natural log of 5 squared. And then on the bottom it'd be the natural log of 5 minus the natural log of 3 to the third. And then on top this would be the natural log of 3 squared is 9. The plus turns back into multiplication. 5 squared is 25. And on the bottom of this would be the natural log of 5 divided by 27. And then this cleans up to the natural log of 225 divided by the natural log of 5 over 27. So we can type it out in the calculator. Natural log of 225 divided by the natural log of 5 over 27. And we get that the approximate answer is negative 3.2116. Or guys, like I said, you don't really need to do any of this. You can just type this in your calculator. Now it just requires a little extra caution. So if I want to type it in all at once, here's how this would go. It would be parentheses 2 natural log 3, close that logarithm, plus 2 natural log 5, close that logarithm, close the top of the fraction, divide by, open the bottom of the fraction, natural log of 5, close that logarithm, minus 3 natural log of 3, close that logarithm, close the bottom of the fraction. And if you type it in all at once, you'll get negative 3.2116, which is the same answer we got by doing all this condensing. If you're comfortable with typing all this in, that's fine. If you're more comfortable with condense it down to smaller numbers and then type it in, that's fine also. Either way, guys, on the exam, you'll need to give the exact answer. And either one of these would qualify as the exact answer. This one or this reduced version. And then you'll need to also, I'll say, give the approximate answer out to 4 decimals, which is the negative 3.2116. Alright guys, after this we've got one more video. I should have that posted in the next day or so. Anyways, hit me up with questions. And guys, we'll get the last exam in sometime next week.